Hello and welcome to the first HackSoc talk of the 2023 academic year. My name is Joseph Christek Walton, I'm full of coronavirus, and for the next 30 minutes I'm going to be telling you about the surprising depth of research put into Pushdown Automata and the variations thereof. So last year I did my final year project for my bachelor's degree, the goal of which was to make an automata simulator that was easier to use, more accessible and more well-rounded than the ones currently in use. The main automata it was simulating was the Pushdown Automaton, which I'll explain in a bit, as I felt that would be the sweet spot for complexity between the ones beneath it and the ones above it. Whilst it didn't quite meet all the requirements I set myself, 6 months is a shorter time span than you think, I did end up learning a deal more than I expected about the Pushdown Automaton. Not only are there several, but they're still being researched to this day. This struck me as quite a surprise, as I imagine it will do for most of you, as I'd only ever known about the Pushdown Automaton, and it seemed like a disservice to these researchers that CS Education only touched on it as a stepping stone to the golden child that is the Turing machine. Hopefully, by the end of today, you'll be somewhat more aware of the versatility of the Pushdown Automaton. But we're getting ahead of ourselves. First, the CS students who are uninitiated, the non-CS affiliated, and those who just need a refresher, what exactly is an automaton? Or state machines if you've got a word count to hit, are abstract models of, well, whatever you want really. Historically they've been used for nerve nets, cells, computer behavior, artificial intelligence, robotics, linguistics, it goes on. Generally, if you have something that changes in some way when information is fed into it, you could model it. One of the most basic automata, the finite state machines, are made up of states and transitions, states being what state the model is in, and transitions being how the model can change from one state to another. Sometimes the model is only good if it stops at a certain state, however, as we're going to get into, there's a lot of ways this can be changed. As an example, I've made an automata for a light bulb, or just any machine that turns on or off. As you can imagine, it has two states, on or off, and it can be transitioned between these states by flipping the switch. The action of flipping the switch is represented by a 1 here. As a person who pays for his bills, I've made this model such that it starts with the light switch off and only accepts inputs that end with the light switch off. If you flip it once, that won't get accepted, as it will halt on the on state. If you flip it twice, then it will get accepted, as it will halt in the off state. Another thing you need to know about automata for this talk is that each one has a language, which simply put is a set of inputs to be accepted by the automaton. Sometimes the set is just a list of strings, but in the case of this light bulb, we can represent its language as a reject statement, that being 1 in closing brackets with a wildcard or a clean star on the end. This is useful for if you could have a potentially infinite number of languages, since you can't write them all out. There are different sets of languages of different sizes which correspond to different types of automata. And when I say different types, I don't mean different as in they have different states and transitions and all that, but that they're fundamental functionality changes. These changes in functionality enable the automata to be able to represent increasingly complex languages, such is the case with the Pushdown Automaton. So now that we know what an automaton is, what exactly makes something a Pushdown automaton? Formally introduced by Noam Chomsky in 1962 for, of all things, linguistics, the Pushdown automata, or PA as it will be referred to in text, is an automata that has a crude form of memory, that being a stack. A stack is exactly how it sounds. It's a data structure in which you put new data on the top, known as pushing, and remove data from the top, known as popping. It's also known as a first in, last out structure, since the first data you put in is the last data to be removed. For this talk we'll use the term stack, as we already have enough acronyms and abbreviations in the field. The transitions on a PA include the input like before, but also the string with a slash in it. On the left side of the slash is the value we want to pop from the top of the stack. If it's there, and the input matches of course, we can use this transition. The value on the right is what we want to push to the stack, operating from right to left. We can push the same value, add a new one, or remove the value. When we get to the next state, the stack will have been affected somehow, which has massive implications for functionality. The set of languages the set of language PAs accept are known as the deterministic context-free languages. For those of you who know about PAs, the issue of that statement, sit tight, I'll get to that, which are a superset of the languages accepted by the basic automata I showed you before, the finite state automata. These regular languages. We know that the PA languages are a superset for two fundamental reasons. Every regular language can be accepted by some PA, and there's at least one context-free language that's not regular. Proving the first point is easy. You will have seen an example on the previous slide. Just make a pushdown automata that ignores the stack. Here's that light bulb model again, which is a regular language represented with a pushdown automata. As you can see, it makes no changes to the stack whilst the functionality is preserved. To prove the second point, that being there's at least one context-free language that's not regular, I'll show you a new automata with the language 1 to the n, 0 to the n, where n is a integer bigger than 0. The finite state machine has no way of accepting this exact language, as it can't remember how many ones it's seen when counting the number of zeros. But the PA, with its stack, can do this. Hence, the PA set of languages is a superset of those accepted by the finite state machine. So one thing you've got to know is that pushdown automata are weird. To round out the main three, since I've introduced you to finite state machines and pushdown automata, the big one right at the top is the Turing machine. And generally, now that I've told you what that is, let me tell you why it's an absolute non-conformist when it comes to automata. And in at least two common rule changes, the pushdown automata's set of languages changes where the finite state machine and Turing machine's languages don't. The first of these rules is being deterministic versus non-deterministic. In a deterministic automaton, states cannot have any duplicate transitions. That being, the transitions can't accept the same input stack head combination, etc. In a non-deterministic automaton, states can have duplicate transitions going to the same target state or otherwise. Whilst non-determinism can make your finite state machine or Turing machine smaller and more readable, they're only able to accept a greater number of languages. Pushdown automata, however, are able to accept all the context-free languages rather than just the deterministic ones from before. This can be proven in much the same way with the binary palindrome checker. In short, the reason for this is because a pushdown automata, deterministic or not, has no knowledge of when it's past the halfway point of an input, unless you were to put a separate character there as a marker. What makes the non-deterministic pushdown automata more capable is that it can try out every single point in the ring as being the midpoint until it finds the correct one. Each attempt will affect the stack in different ways. The finite state machine has no stack to affect, and the Turing machine is already capable of all computable languages, albeit with different speed and space constraints depending on if it's deterministic or not. As you can see here, pushdown automata messes up a lot of times before it gets it right, and that's the benefit of a non-deterministic pushdown automata. The second thing you can do to all three of these is change how the input string is navigated. What I've been showing you so far is just going from left to right on the input, like you're reading it. That being, you have a character, once you've read it, you move on to the one to its right. This is not the only way of navigation. You can move left, right, or stay in the same spot, as long as it stays within the bounds of the input. Once again, applying this rule to pushdown automata causes their set of accepting languages to change, unlike the finite state machines or the Turing machines. Furthermore, the set of languages accepted by the deterministic two-way pushdown automata is a superset of those accepted by a one-way non-deterministic pushdown automata. It accepts the context-sensitive languages, as well as the context-free ones. An example of a context-sensitive language that's not context-free is a to the n, b to the n, c to the n, or represented here, in a similar manner, 1 to the n, 0 to the n, 1 to the n. A one-way non-deterministic pushdown automaton cannot reliably accept this language, as it has no way of remembering the value of n. That is to say, compare the length of the 1 strings to 0 strings, after passing the 0. A two-way deterministic pushdown automata can do this, though, by simply moving the input head back to the start of the zeros and treating it like there's only been 2 character lengths to compare. But enough of the generalist modifications. What are some things we can do to the pushdown automata that can change it up? Well, we can always start with its defining feature, that being the stack. Notably, the number of them. We're familiar with a zero-stack pushdown automata, as that's just a finite state machine, and we've seen what a one-stack pushdown automata can do. What if there was a second stack? As it turns out, adding a second stack will allow it to accept recursively enumerable languages, the same set of languages accepted by a Turing machine. Granted, a two-stack Pushdown Automata will never be as quick, which is to say using as few operations as possible, compared to a Turing machine. For an incredibly brief rundown of a topic that could warrant its own talk, the Turing machine is an automaton that affects a tape of infinite length onto which an input is loaded. It can move left or right, overwrite characters on the tape, or add new ones to the front or back. This functionality can be recreated with two stacks. Prior to the intended operation, you will need to load the input of your Pushdown Automata into one of the stacks. From here on out, call this the before stack. Once loaded, you can move characters from the before stack to the after stack to simulate the process of moving left or right. Furthermore, changing the character as it's moved between stacks replicates the overwriting behavior. I'd show you an example of a recursively enumerable language that isn't context sensitive, but that particular group of languages requires polynomial amounts of space or time, and thus are far too scary to be presented as an animation, so you'll have to take my word for it. Adding credence to this, I did try and make an example of just two-stack Pushdown Automata messing around. However, it crashed twice. This is the second time I've made this presentation. With a pattern of increasing stacks leading to increasingly large sets, it begs the question, does adding another stack add any further increase in language set size? No. The boring reason for this is that Turing machines accept the largest set of languages possible, thus the recursively enumerable languages are the limit to computability. The interesting reason is that you can simulate 3 stacks on 2 stacks. This can be done by representing the values of each of the 3 stacks as a pair, which stack it belongs to, and the value. We refer to these as stacks A, B, and C. For the stack pair we're using to simulate A, B, and C, the first stack will be used dedicated to A, and the second will be for B and C. When popping from A, you pop from this first stack. Typical behavior. When popping from B or C, however, you need to get a little involved. Pop the values of the second stack, moving them to the first stack temporarily, until you find the stack pair that matches the given value and given stack. Pop that for real, then move all the values from the first stack that were being temporarily stored back into the second one. The same can be done for simulating 2 stacks on one, as you can imagine, since you need the temporary storage. Another modification you can make to a Pushdown Automata is reading the stack. Now we can't change how we write to it, otherwise it no longer be a stack, and thus the automata will no longer be a Pushdown Automata. However, being able to read any character in the stack does not compromise this, and is indeed what the confusingly called stack automaton does. Created by Seymour Ginsberg, Sheila Griebeck, and Michael Harrison in 1967 to better represent compilers, formerly done so by Pushdown Automata, the researchers added the ability to step left or right through the stack to read different characters in it. You can still push or pop characters to or from the stack respectively, but only if you're in the rightmost position of the stack. At this point you might be thinking, well, why don't we just use a Turing machine? They'd existed for decades at this point after all, and would be more than capable of compiling code. The reason against using Turing machines is that they're more committed than most to the whole abstract machine concept. That being, they're not practical in the real world with their infinite tapes and such. The linear bounded automata, a restricted version of the Turing machine, is a much more realistic model of the computer as, like the name suggests, the tape is bound to a certain length. This would be capable of being a real-world model of a compiler. It should therefore come as no surprise that the stack automaton accepts the same set of languages as the linear bounded automaton, those being the context-sensitive languages. An advantage to using a stack automaton against a linear bounded automaton is that the linear bounded automaton has a limited memory size, whereas stack automaton does not. The proof of equivalence to context-sensitive languages was in the original paper. However, a short 7 months later, John E. Hopcroft and Jeffrey D. Ullman were able to prove that it was actually capable of more than this, once again with determinism and non-determinism providing different results. We're at the point where regular language sets are a bit more specific than the ones we've had so far, regular language, context-sensitive, etc., so we're going to need a quick complexity classes tangent. So a complexity class is the set of languages that some kind of Turing machine can solve, given a restriction to either the space or time the Turing machine can use. Now when I say time, this just means how many states it can do before it has to halt, And when I say space, that's how many positions on the tape can be written to, or for a push-down automata, how many it can hold. The amount of time or space can be constant, or it can be relative to the input's length. For example, nspace 30 is the set of languages accepted by a non-deterministic Turing machine with 30 spaces on the tape available for writing. Context-sensitive languages will be defined as nspace n being the length of the input. It's the linear big O notation, which makes sense for the linear bounded automaton. Now, intuitively, a larger amount of space allows for a larger number of functions to be computed. Going back to nspace 30 and nspace n, we can prove the linear one is a superset of the constant one by simply using a function where it's required for the whole input to be loaded into the memory and have an input of length 31 or higher. This stands for the other sizes indicated by O notation. With that established, in this second paper, it was proven that the deterministic stack automaton is equivalent to d space n log n, and a non-deterministic stack automaton is equivalent to n space n squared, quadratic non-deterministic space. Whilst the jury's still out on whether d space and n space are equivalent exactly, it can be safely said, just based on the big O notation, the non-deterministic automata languages are a superset of the deterministic counterparts, which are in turn a superset of the context-sensitive languages. One thing before you move on, an important distinction made in these papers is that they look at non-erasing stack automata. These are stack automata that do not remove values from the stack once added. At every pop, at least, the same character is being pushed. This is due to the motive for creating such an automaton, that being to compile code. Ideally, a compiler wouldn't overwrite work it had done already. I couldn't find much on the specific capabilities of erasing stack automata and how it compares to non-erasing ones. So, enough messing with the stack. How about we mess around with the accepting conditions? In 1981, Ashok K. Chandra, Dexter C. Kozin, and Larry C. J. Stockmeyer, working for IBM at the time, presented a paper in which alternating automata were introduced. These were non-deterministic automata that split their states into existential and universal. We're already familiar with existential states. These are states that require one immediate connection to lead to an accepting state. Notably, the immediate connection itself does not need to lead to an accepting state. It just has to be connected to a state that is one or a state that connects to a state, and so on and so forth. Universal states require all their connections to lead to an accepting state in order for the input to be accepted. Importantly, if a universal state has no connections, then it only requires itself to be accepting. In a way, this sort of redefines the automata framework, which this talk is the first time you've ever been told about automata. I'm deeply sorry for having told you two definitions, as accepting states can now just be universal states with no connections. Anyways, alternation is like non-determinism and being two-way in that it can be applied to multiple automata. Pushdown automata being one of them. Whilst hardly the focus of the paper, that being, of course, the Turing machine, they did take the time to establish that the set of languages accepted by an alternating one-way deterministic pushdown automata is equivalent to exponential deterministic time, time being the number of operations relative to the input length, or exp time. So how does that compare to other pushdown automata? Comparing classes of time and space is not as direct as just time to time or space to space. However, we do know that exp time is at least equal to polynomial space, that being d space n to the c being a constant, n being the length of the input. We'll start from the other end, a deterministic Turing machine which has a tape that is bound to some polynomial, c, of the input length n, i.e. its n to the c space is long. We'll give it a binary alphabet, that meaning that the input characters can only be 0 or 1, since binary can represent other numbers and characters, see computers. With this alphabet on the bounded tape, we can safely say there are 2 to the n to the c possible strings that could occur on this tape. On top of this, there are n to the c spaces on the tape the pointer could be in, and another constant s representing what state the Turing machine was in. If we keep the Turing machine deterministic and insist that it holds, then the way to maximize time here is to have the tape have every possible string with every possible input head on the tape and in every possible state, which is kn to the c, 2 to the n to the c. Since it takes one step to reach each configuration, that means we will need this number of steps to complete, and as this is a constant raised to the variable that is the input length, it qualifies as exponential time. At most, dspace enter c is equal to exp time. As for the limits of space for exp time, well, that would be exp space, as you could have one space for every step in the automaton. This would suggest that exp space accepts a larger number of languages than dspace, since the upper limit of exp time is exp space. Hence, the alternating pushdown automata is the most capable pushdown automata we've seen today to only use one stack. So, to wrap up this rundown on pushdown automata variants, we'll have a look at one that was proposed this century. The visibly pushdown automaton, also known as an input-driven pushdown automaton, was proposed in 2004 by Rajiv Allur and Parthasarathi Madhusudan. Or more specifically, they proposed the class of visibly pushdown languages using a pushdown automaton with extra rules. The rules for this automaton are the same as standard pushdown automata, except the input character you read dictates how you interact with the stack. The visibly pushdown automata has 3 alphabets: call, return, and internal actions. These alphabets are disjoint, meaning characters must be unique to their alphabet. If the character reads is from the call alphabet, a character is pushed to the stack. From the return alphabet, a character is popped. And for an internal action character, the stack is kept the same. Notably, the input character read is pushed to the stack. This takes control of the stack out of the automaton designer's hands and instead falls entirely on what the input is. Excuse me. A question you might have, and by that I mean a question I had when I was reading the paper, was if I, designing a visibly pushdown automaton, can't control what gets pushed to the stack directly, then what is the point of having the stack? The thing to remember is that yes, you can't control the stack, but you can control the call alphabet and the transitions between states. You could have multiple transition options depending on what is currently at the top of the stack and what character you want to push. So, how capable is this kind of automaton? Breaking the trend of the talk so far, visibly pushdown languages, the languages accepted by a visibly pushdown automaton, excuse me, are actually a subset of the context-free languages, which you will remember are the set of languages accepted by a non-deterministic pushdown automaton. An example of this is a language 0 to the n, 1, 0 to the n being some positive integer. This would be simple for a non-deterministic pushdown automaton, as seen here. Furthermore, you can make it a deterministic pushdown automaton, as seen here. You can't make it with a visibly pushdown automaton though, as it requires 0 being both a call and return character, which is not allowed. That being said, if you're willing to completely change the input, you can replicate the context-free language. Let's look at the example again. 0 to the n, 1, 0 to the n. There are 3 things happening when this is being processed by the automaton. Read 0, push a character. Read 1, do nothing. Read 0, pop a character. It's a list of pairs of characters and actions. Now, if we map those pairs to a unique character, then a VPA can run it. For instance, read 0, push becomes A, read 1, do nothing becomes B, and read 0, pop becomes C. We then add A to the call alphabet, C to the return alphabet, and B to the internal actions alphabet. Now if you translate your input to AN, BCN, you can accept that language. This doesn't really change the acceptance of visually pushdown languages though. Visually pushdown automata even. It's still a different language at the end of the day, even if it is translatable, and the translation itself cannot be done without knowing the language is context-free and being able to modify the input or store on the stack, which are things that this type of visually pushdown automata can do. So visually pushdown automata sit somewhere below deterministic context-free languages, making them the least capable automaton we've seen today. It begs the question then, why was a paper written about this, and indeed continued to be written afterwards? So there's a couple more properties about languages in general that I need to tell you about. Closures and decision problems. Closures are properties of language sets that say if you do this thing to the language in this set, it changes to another language in the same set. There's a ton of closures that are used to test the capabilities of a language set. One of the most straightforward is the union closure, which is basically if you have two languages A and B that are in the same language set, and you take all the strings from both languages and make that a new language C, C will also be in that same language set. Closures are important both in the sense of simply learning more about these sets, but also in the case where automata are used for real-world applications. The more closures a particular language has, the more flexible and stable it is for real-world purposes. If you had a compiler, like the stack automaton researchers were writing about, and wanted to add another program to happen immediately after it, you want to know if the set of languages of a stack automaton are closed under concatenation for certainty that it could be done. Regular languages, represented by the finite state machine, have so far had the most closures of any language set. They're closed under union, intersection, complement, concatenation, and clean, and many others, but these 5 are relevant for now. Context-free languages are only closed under union, concatenation, and clean star, and deterministic context-free languages are only closed under complement. Linear bounded automata are closed under these, and Turing machines under some of them. Visually pushdown languages are closed under all 5, just like regular languages, even though there are a superset of them, giving them the most closures of any pushdown automaton thus far. As an example, I'll apply all 5 to that language we made before, a to the n, b, c to the n, as a new one, b, b to the n, where n is even. Or rather, just n is a number. So we'll start with the union, which is again where n is even. So we'll start with union, which again says for 2 languages A and B in a given language set, you can have a language C that contains all the strings from both A and B that also appear in the same language set. You can do this by having the visually pushed down automata be non-deterministic and have it branch off into the separate automata when the languages start to diverge, as seen here. If you already had a characters, you're locked out of the B language, since the top of the stack needs to be the default character. Likewise, you'll always fail if you try and run language B on string on language A parts. Intersection is basically for any 2 languages A and B in a language set, if you take the strings that only appear in both languages and make that new language C, that will also be in that language set. This one's pretty easy, albeit a bit of a cop-out. Language A contains string B for when n equals 0. Language B contains a string B again for when n equals 0. Therefore, we need a visible Pushdown automaton that accepts exactly one character B, as can be seen here. Complement states, for a given language A, in a given language set, it is complement, which is every single string minus that language, will also appear in the language set. Complement here is referring to every string that will not appear in the language. Using a to the n, b, c to the n again, the common factor of all its strings is that they all contain exactly one b and the number of a's is equal to the number of c's. A fairly straightforward way to find a language's complement is to take its equivalent automaton and swap the final states with the non-final states. It's important that the automaton is complete, meaning it includes transitions for invalid inputs. Modifying the example to be complete and inverting it, we can see a to the n, b, c to the n's complement here. Concatenation is, for given languages A and B in a given language set, language C is also a language from that set made up of the string S complement, where S is the string from A and S complement is the string from B. This one is very much the case of having the language B automaton start after automaton A once the conditions of A have been fulfilled. When running the second one, the first automaton stack alphabet, as is left at the end, is treated as the bottom of the stack. Finally, clean star is for a given language A in a given language set. Language A star is a language in the same language set that accepts every possible combination of the character in A's alphabet, or in this case, alphabets, being a visually pushed down automaton. Using A to the n, B, C to the n as L clean would be a case of having one state with the transitions for each character. Notably, all the characters must be turned into internal actions, as if we kept A as a call and C as a return, then there's a limit on the number of C's. So that's closures, something that visually pushed automata are better at than its more capable counterparts. The other thing I mentioned were decision problems in the context of automata theory. These are basically true-false questions that say, will the automaton give a definitive answer, i.e. it halts when doing X, Y, or Z? An example of a decision problem is, given a number X, is there any automaton that can definitively say that X is prime or not, i.e. will it halt on every input? The OG decision problem is the Entscheidungsproblem, a German word meaning decision problem, proposed by David Hilbert in 1928. The problem was extremely broad, asking, given any statement, whether mathematical operation, some mechanism, etc., can we definitively give a yes-no answer for it? This was the question that led to Alan Turing creating the Turing machine to help find an answer, to which it was a definitive no. But that was a story for another time. Since then, there have been some decision problems proposed that can be answered, depending on the automaton you use. Three notable ones are the emptiness problem, is there an automaton that can accept no strings whatsoever? The universality problem, is there an automaton that can accept every string ever? And the inclusion problem, for any two automata, can it be proven that the language for one is a subset of the language of another? As with before, finite state automata are more than capable of deciding all three problems. Deterministic pushdown automata are able to solve just the emptiness and universal problems, and the non-deterministic one just the emptiness problem. Visually pushdown automata are capable of all three, although it does require more resources than its finite state automata counterpart. The visually pushdown automata requires exponential deterministic time, the same as the other pushdown automata, simply on account of it being a pushdown automata. Correction, that is polynomial time. We'll prove inclusion first, as the paper uses this to go on to prove the visually pushdown automaton's universality. Proving that a visually pushdown automaton's hold for inclusion problems requires one of the closures we used before, those being complement and intersection. Given two languages, L and M is complemented, which is then accepted every string that doesn't appear in M, and then intersected with L. Then we simply run the new automaton N to see if the language set is empty. Considering that we run every language against every other language, including itself, this will take exp time, as it's the exponential of the number of languages. Proving the universality problem is simply running the inclusion problem proof, with L being a single-state visually pushdown automaton that accepts every string, much like a clean star closure from before, and M being some other visually pushdown automaton language. Thus, whilst it doesn't measure up in terms of language set size, the visually pushdown automaton is able to introduce some of the desirable properties of finite state automaton to the pushdown automaton framework. So, that was a brief look into the research around pushdown automata. Indeed, it goes a lot deeper than what's been covered today, finding better proofs for closures, language sets, and decision problems, combining the different types of pushdown automaton to see how behavior is affected, and inventing new types of automata, like the quantum pushdown automaton or the probabilistic one. With that said, thank you for watching. Hopefully I've been able to spark some interest in the field for those who were aware of automata, and successfully introduce it for those who aren't. The animations for these were made using the project I did last year, albeit on a more updated one than the one I submitted. Thank you all for watching.